welcome. I'm Jean-François Maes, and this is probably the longest title you'll ever see on a presentation. So it's a trip down history lane on how to defeat EDRs in user mode, how to do it using the Invoke, and how these conference talks inspires others. So without further ado, let's talk about the story on how this presentation came to end. So a few months ago, I actually did a similar presentation for the company I used to work for. It's called Inviso, and it was posted on YouTube. And then after a few weeks, I checked my Twitter, like probably most of you do, as InfoSec news travels faster around Twitter. That's what we all do. And I saw this tweet from a guy I've never heard of. His Twitter handle is ClassVirus. And he said, blog post +2 release. It said AV and EDR bypasses in like the tweet. That interests me a lot because I'm a red teamer. So EDR and EV bypasses is kind of my jam. I opened the blog post and I actually see my name there as well. Jean Maes, so that's me. And I was pretty surprised by this. I looked into the code, I liked it a lot. And then I actually reached out to ClassVirus. He's actually right here. And I told him, hey, why don't we combine forces and present together? Because I like the tool. You use my techniques in your tool, so let's just do it. Let's collaborate. And that's how that ended up. So what are we actually going to talk about? Well, I actually made a short video to tell you.
Has this ever happened to you? You have been hired to do a penetration test and need to get a reverse shell or other payload on your target, but the antivirus or EDR is in the way. Today is your lucky day. In the next 45 to 60 minutes, John and Alessandro will walk you through the history of cybersecurity and tell you how modern adversaries evade alerts in userland. So sit back and enjoy the presentation.
So yeah, that's a small advertisement. I actually hired someone to do the voiceover, and I can't imagine what that guy must have felt like when actually talking about that stuff. But yeah, he got a small payday out of it. I used Fiverr to do this. So yeah, no questions asked. He just talked about it, and yeah, there you go. So my name is Jean-François Maes. I'm now a senior consultant at TrustedSec. I'm also a SANS instructor. I teach the Security 699 Purple Team. So if you want to talk about SANS, Purple Teaming, or Red Teaming, come see me after the talk. I love socializing, so there you go. You can also find me on Twitter, LinkedIn, on GitHub. And I publish barely working tools. That's also my Twitter. If you follow me on the Twitter handles, you'll actually see in my banner, I like to call myself a tinkerer. I publish code. It doesn't always work as intended, but usually it does. I just do this because I like learning and coding at the same time. I like sharing knowledge as well. So if you see some code examples from me, you can definitely check it out on GitHub. And then yeah, I have my co-presenter here with me.
I'm pleasure to meet you. I'm Alessandro Magnosi. I'm a senior security consultant. I'm working for BSI. BSI is a nice environment, nice company. It's a big company actually. It's involved with standards, like for the most part, ISOs, as you know it. And we're also involved with training cybersecurity, like deeply in cybersecurity, and we're offering services ranging from common pen testing to reverse engineering, threat intelligence, and also adversary simulation. On top of this, I'm a bug hunter for CNAC Red Team, and like in my spare time, I really like coding, so I really like publishing offensive tooling and tradecraft. As my co-speaker, also my code has some issues at times that I love to solve. So on internet I go with the handle ClassVirus, both on Twitter and GitHub. If you want to reach out, if you want to test the code that we are presenting today, just please go on the repository, fork the repository, and just submit issues if you find, or like ideas or whatever, because everything is very well appreciated. And if you want to reach out on Twitter, I'm always open to conversation, so feel free to.
There you go. Right, so this is a bit of the calendar here today. So first of all, before I start talking about fancy EDR bypasses, I'm going to take you on a trip down memory lane, talk about how antivirus solutions and EDRs by extension evolved over time. Then I'm going to give you a very short and small primer about the Win32 API, because in order to actually bypass EDRs, you first have to understand how malware actually works. I'm also going to talk about the Invoke, which is probably my favorite framework out there. It's written in C#. I like high-level languages. So C# is definitely one of my favorite languages as well. And the Invoke is specifically designed to tackle these problems that we're going to talk about today. I'm also going to talk about manual mapping and syscalls. So if you don't know what those are, don't worry. It will be clear in just a few moments. And then my colleague Alessandro will also talk about some things today. So Alessandro, if you want to talk about it.
So my part is actually on, like, after we will see, like, specifically userland hooking and techniques to bypass userland hooking, we will actually go back a step and see how we can actually make our payloads and malwares better. And so we start from basic things. Don't forget the basic to not get caught in an early stage. And then we will, like, step again on userland bypass and other kind of ways to blend in with our target so that we are, like, probably, like, pass through even highs of, you know, less experienced OPSEC guys. So, and then at the end, we will bring in automation and we will show you a framework that you can use, test, and extend to build automatically your payload that will build automatically bypass EDR and AV. And when you say EDR, userland hooking and AV solutions.
All right, thank you, man. So let's first talk about a trip down memory lane and how it used to be when I wasn't even hacking yet. But I heard stories, of course, by people who are way more experienced than me. So what used to be the case was, this was in terms that Metasploit and the Meterpreter framework was brand new. You could basically just generate a payload in Metasploit framework, drop it to disk, double-click it, and you would have a reverse shell. Antivirus wasn't really a big thing by then. And the obfuscation methods that the Metasploit framework has used to work very, very well. Still does sometimes. And you could just bypass any antivirus if there was actually already an antivirus installed in the first place. So happy days, not a lot of effort that you had to do. You could basically be a script kiddie and compromise networks that way. Then Microsoft, especially when the PowerShell started getting more and more abused, they actually caught on to this quite rapidly, and they introduced AMSI. So if you don't know what AMSI is, it's the anti-malware scanning interface from Windows, which actually helps defend against script kiddie attacks. So if you don't know about AMSI, it's basically a DLL that is injected into any process that is getting spawned. It's also in userland, so you could actually manipulate that. As you can see right here, that's what I did. It's really not that hard if you know a little bit about the Win32 API. You could just override the pointer to the AMSI scan buffer and make it throw an error, which makes it impossible for your AMSI to actually get scanned. So your payload wouldn't get scanned, and you would actually bypass it, as you can see right here on this slide. So that actually made the cost of intrusion a bit harder, because attackers now have to deal with some defensive measurements, and they actually need to understand a bit how the Win32 API works in order to try and bypass AMSI. Now, of course, there have been automation frameworks out there to try and automate this for you. Most notably AMSI.fail, which was actually made by a colleague of mine, also at TrustedSec, called Melvin Langvik. But, of course, the publicly available AMSI bypasses, they work for a few moments. They work for maybe a week, maybe a month. If you're lucky, a year. But eventually, time catches on, and defenses will actually trigger on the publicly available AMSI bypasses. So it is in your best interest to learn how the Win32 API works, so you can actually do that by yourself. As you can see here, this code was actually written in about 15 minutes. So it's not that hard, and there's not really a lot of obfuscation going on here. As you can see here, like load library, I just split AMSI, so A plus MS plus Haxor, and Haxor is just I.dll. If you combine those, that's just AMSI.dll. There's not really a lot of obfuscation there, but this is enough to actually bypass AMSI. Why? Because this is just, quote-unquote, customly made. It's not just publicly available on GitHub. So it takes a bit longer to actually detect this, right? Because this bypass is not getting used very frequently, which makes the shelf time a little bit longer. So it is definitely in your best interests, if you are an adversary or you do adversary emulations, that you actually learn how to do this by yourself. And then, of course, this is the current era. We have EDRs now. It's a lot harder for adversaries to actually breach enterprises when EDRs are correctly implemented, because that's another story. Sometimes enterprises do have endpoint solutions available to them, EDRs available to them, but they are not really configured correctly, especially when we're talking about C-level, like C-level suites. Then defenses tend to get a little bit lowered because they don't want the complexity of retyping their password all the time. And of course, there are other things to deal with as well, such as attack surface reduction, application whitelisting, and exploit guard. But never fear though, because if you know the Win32 API, you can start manipulating things and you can try and craft your bypasses. But in order to do that, you first need to understand a little bit how the Win32 API works. So Windows actually, well, not Windows, Microsoft has a publicly available API calls documented online that commonly is getting referred to as the MSDN. So if you go to the MSDN and you look for an API call, let's just say virtual alloc, you would actually see the function declaration of virtual alloc. Usually it's written in C or C++, but you can translate that to any language you want. And in order to fully understand how it works, you need to understand ntdll.dll, because this DLL is very, very important. We are going to talk about ntdll.dll quite a lot. And it's quite of a tongue twister as well, because ntdll.dll, so you can hear that quite a lot. Why is this one important? Well, this is actually the bridge between what we refer to as userland and kernel land. So Microsoft, Windows, runs, of course, on your operating system. So your operating system has CPU, of course, and that is being managed by the kernel, right? As a regular user, you can't just interact with the kernel directly. There are protections around that, so you can't just start manipulating the kernel directly. What you can do, however, is spawn new processes. These processes are being spawned in what we call userland. So everything that is accessible to a user is living in userland. Now, how do CPUs actually interact? Well, they actually see the userland application being spawned, and there are API calls in the backend, usually NT APIs, so that's actually prefixed by the words NT, but also ZW, and those are actually talking to the kernel directly. So if you, as an adversary, know about ntdll.dll, know about all the exported functions that ntdll.dll exposes, learn about those prototypes, so the function prototypes, which are not documented on the MSDN, by the way. But if you know about these stuff, then you can actually start manipulating it. And if you are that low level, you're actually just one level above the kernel. That's actually where EDRs also place their hooks. So if you know how to manipulate that, you can avoid userland hooks, and you can actually still run malicious payloads on the environment with even endpoint protections in place. So that was a lot of theory, but let's just look at a practical example right now. So these are some API calls that are commonly used for process injection. So shellcode injecting into a process that's already alive. So what are the API calls? Well, virtual alloc. This is used to allocate memory into the process because you are going to inject shellcode. So you need memory in order to actually inject the shellcode. So first you need to allocate some memory. Then virtual protect. Why do you need virtual protect? Well, you need to actually allocate memory, but you also need to have writable access to that memory, because if you can't write to it, you won't be able to inject your shellcode into it. So that is what virtual protect does. Then you have write process memory. Guess what? That is writing operation. So you're going to take the shellcode and actually write it into the memory that you just created, and then create remote thread. What's that going to do is you're going to point to the shellcode that you just injected, and you're going to say to your program, dear program, please create a new thread and use this new code as your entry point. So you would actually create a new thread that is going to launch your malicious code. So what happens if you create a loader that calls ntdll.dll when your EDR hooks kernel32.dll? Well, deal with it. Why? Because I said ntdll.dll is the lowest you can go from user mode. So if your EDR actually hooks above that, let's say kernel32.dll, it's actually not going to catch anything you use because you are using ntdll.dll. If that doesn't make a lot of sense yet, don't worry, we're actually going to see the call tree in just a few slides, which makes it more clear. So Rastamaus, I don't know if you know him, he's quite famous because of AMSI bypasses, and he also has a red team operator course, which I highly recommend, by the way, if you're into red teaming. And as a rule of thumb, you always want to go as low as you can. So your user mode, the lowest you can go is ntdll.tll. So this is actually why. In this slide, you can actually see that we are calling virtual alloc x. Virtual alloc x is actually an exposed function from kernel32.tll. But if you see in the call tree, virtual alloc x is actually nothing more than just a high-level wrapper around nt allocate virtual memory. Nt, that should ring a bell. Nt means it's actually an exposed function from ntdll.tll. So that means that if you actually call nt allocate virtual memory yourself, so if you know the function prototype and you start coding your own nt function, you don't have to call virtual alloc x. So if your EDR is hooking virtual alloc x, it's not going to see the call below that. However, if your EDR hooks nt allocate virtual memory, it is going to see the virtual alloc x as well, because virtual alloc x in the backend is calling nt allocate virtual memory. So I hope that kind of makes sense. The same goes for write process memory. That actually calls two nt functions in the backend. So from an EDR perspective, from a defender perspective, it makes a lot of sense to hook nt functions, because then you have telemetry on all the API calls that live above ntdll.tll. EDRs or malware. Why do I say that EDRs or malware? Well, because EDRs are actually using the same methods that malware developers are using as well. EDRs inject their DLL, much like malware would inject their malicious DLL, into any process that is getting spawned. Why does it do that? Well, it does that because it wants to hook certain API calls, because that way they know whenever an API call is being called, it can actually go through their scanning engine, and then they will make informed decisions whether or not you're actually doing something malicious or not. Because every single program that is running on your operating system needs to interact with the Win32 API one way or another. Otherwise, your kernel wouldn't know what to do with your program. So that is why EDR vendors need to inject their own DLLs into any process that is getting spawned. So this is an example of userland hooks. So that is exactly what I said with EDR vendors hooking NT functions. So here on the top side of the slide, you actually see how the disassembly of NT allocate virtual memory actually should look like. And it's always the same with any NT function, by the way. So there's going to be a move instruction from R10 to RCX, EIX to 18H. And the 18H here is important because that is what we call a syscall number. So this 18H is actually the representation of NT allocate virtual memory. This is the only thing that changes in any NT function. So if I would want to call NT write virtual memory, then R10 to RCX is still going to happen. AAX is also going to have the move instruction, but the hexadecimal there, the 18H, would change to, for example, 21H, which would be the syscall number for NT write virtual memory. And then, of course, you have the syscall instruction, the return statement, and that is how a normal function looks like in ntdll.tll. Now, on the bottom side of the slide, however, this is what it looks like when something is hooking NT functions. So in this example, we actually created our own demo EDR, and we placed a hook onto NT allocate virtual memory, and you can definitely see that those two functions don't look the same anymore. The first instruction is actually a jump instruction to a new memory address. And if you would follow that memory address, you would actually end up in the DLL of the EDR. Because they want to inspect whatever API call you do and try to make informed decisions whether or not your action that you're doing is malicious or not. Then, of course, we have some very good security researchers. One shout out I want to do is to Mr. Unicoder. He actually has a GitHub repository with a list of known EDR vendors and what they are hooking on. So he created a script that is actually going to scrape ntdll, so all the exported functions, compare it to the function prototype that I showed you here in this slide. Oh, sorry. This slide. So the move instructions. If it differs from this, so if it differs from the opcode, they know, or he knows, that that function is hooked. So on the right side, well, my right, yeah, your right as well. On the right side, there's a CrowdStrike. So these are all the NT functions and ZW functions that CrowdStrike is actually hooking. So if you as an adversary want to do like a malware and you want to use any of these calls, know that CrowdStrike has hooks on those. So CrowdStrike has telemetry if you're using any of these calls. So what can you do? Well, there are two things you can actually do. The first thing is what we call manual mapping. And what this does is, first let's just see how it normally works. So this is the EDR, this is the malware. I am malware, I want to call an NT function. So I'm going to call ntallocate virtual memory X. Well, guess what? My EDR is actually hooking that function as well. So the EDR is going to see my API call. It's going to say, that looks kind of suspicious. I'm going to block your execution, and I'm going to throw an alert. So that is the normal flow. But if I'm a smart malware author, I can also say, okay, look, I know that ntdll.tll is already in my process memory, but hey, I want to create a new ntdll.tll image in my own memory. So I'm going to fetch a clean ntdll.tll from disk, and I'm going to map it in the memory of my process that I'm currently in. Now, this works, but of course you lose all the functionality of the Windows loader because you are manually mapping it yourself. So that means that if you want to call an API like an NT function and you're using the Windows loader, it's going to default to the already mapped NT function. So if you're manually mapping, you have to do calculations and offsets all by yourself. You have to do it all manually or use a framework like the Invoke to do it for you. So if you do it correctly, you can actually say, map a new ntdll.tll in memory, and I want to use API calls from my newly mapped NT functions. So what that means is EDRs are going to place their hooks at runtime. So when you spawn the program, it's going to place the hooks because ntdll is already in the memory space. The hooks will be placed on the regular ntdll.tll. If you manually map a new ntdll.tll from disk, the hooks won't be there. They will be in the original one, but they won't be in the new one. So if I call NT functions from my new ntdll.tll, I can actually avoid EDR hooks. Well, at least from user mode. The other thing we can do, this is another example. The other thing we can do is syscalls. But in order to understand syscalls, I wanted to dumb it down a little bit because syscalls are quite complex. So I just created a very, very simple proof of concept. So imagine I have a hooked function, and I as an attacker know what that hooked function looks like. That hooked function is just going to print, I do cool stuff. It's not really anything special, but I know as an attacker that I want to call this function. I know this function just prints, I do cool stuff. Well, guess what? I can just create a new function called, for example, clone of hooked function, and just take the implementation of the original function, put it in my new function, and just call that function. It's the same implementation, but the clone of the hook function won't have the hook. So if I call hooked function, I do cool stuff, it's going to print it to the console. But if I do the clone of hooked function, it's also going to print I do cool stuff into the console. So from a user perspective, nothing changes. The functionality is exactly the same. However, the first API is getting monitored by the EDR. The second one is not, because I just created it. That's after the process was already spawned. So no hooks are there. Right. So, userland hook bypasses. What can you do? Well, first of all, this is the preferred option, actually, the preferred approach. Don't get flagged as malicious. Of course, this is a lot harder to just pull off because you would have to have the same EDR in your test environment as your target actually has. And if you are a red teamer or someone who is doing offensive research and you actually publish some white papers, a lot of EDR vendors are just going to say, yeah, no, I'm not going to sell you any license because you're actually scrutinizing our EDR, so I'm not going to give you a license. Which makes it a lot harder, of course, to set up labs. On top of that, EDR licenses usually are quite expensive. So if you're a small shop, you won't be able to just purchase all the EDR licenses out there. So chances are that you won't be able to have like a test run with the same configuration that your client has. So it's going to be a bit hard to actually pull this off. But if you can do it, hey, happy days, because you're not flagged as malicious in the first place. So you won't have to do any like fancy bypasses. Of course, you can also unhook the hooks. So if you know that a specific function is hooked, you could actually patch it again, much like the AMSI patch. So you just call the virtual alloc and you just patch it with the original bytes. That will work as well. You can do manual mapping, as I just explained, or you could do syscalls as well. Of course, the caveat with syscalls is that the number changes on every single operating system, but also on operating system version. So, of course, Linux has syscalls as well. Linux syscalls won't be the same as Windows syscalls, and Windows XP won't have the same syscall numbers as Windows 10, for example. So it's really a cat and a mouse game there, and it helps adversaries a lot if you can automate this process or if you can fetch syscall numbers dynamically. Right, so here are some EDR bypasses summarized. This was actually from last month on Twitter. Yay, Twitter. And it's actually really, really well explained, and I kind of agree with this whole approach. So the first one is a technical capability bypass. What is here is some EDRs aren't capable of collecting all the telemetry, right? Because the Win32 API has literally thousands of functions. It's really impossible for an EDR vendor to collect telemetry of all these functions without slowing regular operations down tremendously. So if you can identify as an adversary what the weak spots are, which telemetry is not getting caught by the EDR you're operating against, and you work on those gray areas, you're not going to get spotted by the EDR. Now, the second bypass is actually the EDR configuration bypass. Remember that I talked about C-level suites, which is a typical example where security is getting lowered just because ease of access. Usually you don't want your CEO to complain to you about having to retype his password all day. So it could be that you lower like the security settings on the CEO's laptop for some reason. And if adversaries land on a machine that has security settings that are lower than the regular security settings, you could play in those gray areas once again in order to try and bypass the EDR. And then, of course, everything that we talked about up until this point is number 3, EDR detection logic bypass. So if you can't do number 1 or 2 and you have to resort to number 3, well, then know that manual mapping and syscalls will help you out on that front. And then I give the words to my colleague, Alessandro.
Thanks a lot. Thanks a lot, John. It's a great piece. So, of course, when we are developing a malware, we don't want to forget the basics. Like, yes, we talked about userland hooking, but what's before that? So let's consider what we want to do, what we want to achieve. And usually what we want to achieve is just having, we are departing as an external attacker. We need some sort of payload delivery mechanism to actually take our shellcode back from a source and then execute it on a certain target. And then when we are on the target and we are executing stuff, we want also to be able to, we want to be capable of bypassing the AV. And so we need to actually like install in our payload all the techniques that are needed to bypass the AV installed on the system we are attacking. And after that, if there is an EDR, also an EDR endpoint protection in place, we want also to bypass this EDR using userland hooking bypasses and other techniques, as John was describing before. And after that, we also might want to bypass eyes, like ISIS, that are looking at our payload. And so we need to have some consideration of what we are doing. And we want to install and provide our payload with techniques that can actually help us pass through these ISIS and pass through detection and stay there in their target for a long time. So let's see a few of them. And let's start with the basics. So let's start with analyzing what an AV is and how is, like an AV software is actually a very complex system as an EDR is. But like in a nutshell, what an AV is actually a software based on 4 different components. So the first component would be like something that we can't see. So like decompressors that are needed to decompress the payload we are scanning to be able to actually scan it. Otherwise, if I don't know how to decompress a payload, I can't actually scan it effectively against signatures, for example. Unpackers is more like the same kind of thing the utility is the same of decompressors, but they are different, of course. Unpackers are based to commonly known packers, and they are designed to unpack payload that are packed with this kind of packers. Like, let's think about UPX, for example, which is a well-known packer. So, for example, any antivirus should have an unpacker for UPX to be able to unpack the payload in memory and scan it efficiently. And then there is the part that we all know, because we're constantly fighting against, and is scanners and sandbox. Scanners are mostly divided in two categories, which are on-demand scanner or file system scanner and runtime scanner or in-memory scanners. The difference is that an on-demand scanner or file system scanner will actually play in our game when we want to land a payload in the target. So if we want to install a payload in the file system of the target we are attacking, well, then of course we need to care about this file system scanner, because it will probably just try to take our payload and scan it against its database. The in-memory scanner is a bit more complex, and it's what my colleague was actually already explained. And it's actually, we can think about an in-memory scanner as something that scan a payload, a binary payload in memory. And MSI, for example, is this in-memory scanner provided by Microsoft. What AMSI does is actually installing a DLL into the process image of a process running into the system. And what it will do, it will just, whenever I'm trying to reflectively loading some binary payload, it will just be loaded on demand and scan my payload for common signature. It's still signature based, but like techniques that will allow me to bypass the antivirus back in the day, like reflectively loading some shellcode, won't really work anymore if the shellcode is packed with known signatures. So we need a way to bypass that as well. And the sandbox, for instance, is the more advanced software in the antivirus like world, and it's actually what it is. Like, it's a virtual machine, it's a very little virtual machine that is designed to run my payload and actually understand if the payload is doing something dodgy, and it classifies it. And if it does, it will classify this as malicious, and it will just stop the execution and delete the payload. So what we need to bypass, like when we are attacking target, of course we have different kind of things to bypass depending on what language are we using to actually execute code. So if I'm using .NET or PowerShell, I need to actually care about, because .NET and PowerShell have MSI loaded by default. PowerShell, when you load PowerShell, you have MSI loaded like as soon as PowerShell process is started. Instead, in .NET 4.8 is loaded on demand, so it's actually loaded whenever I'm trying to reflectively load something using assembly load or assembly load from, whatever technique I use to reflectively loading an assembly. The .NET, the CLR will actually inject MSI in the process image, and MSI will scan that buffer. So we need to bypass the scanner. For a native payload, this is not really so important, but we still need to bypass the sandboxing. So after we bypass MSI, we still need to take an additional consideration about the sandboxing, because probably my payload will be scanned, will be just executed in a sandbox, and if it contains any malicious behavior, then yes, it will be detected as malicious. If we want to land on the machine and we want to install a PowerShell script, a .NET executable or native executable, well, in that case, we need to take care also of the static scanner. And so, how can we bypass like we were talking about the real-time scanner? How can we bypass the real-time scanner? So the technique, as John was saying before, is in-memory patching. So we just need to open an handle to the process we are executing, to our process, detect AMSI in memory, detect the location of the function that is actually executing the scan, which is in this case is AMSI scan buffer, and then we will use a patch, an in-memory patch, to just avoid the scan to return a correct value. So even if my payload contains known signatures, if AMSI is patched, it won't be able to scan it. In this case, this patch is actually achieved zeroing out the register that contains the length of my buffer. So if you're aware about how x64 works, so you will have in any function you are actually executing, you will have the parameters put in RCX, RDX, R8, and R9 registers. So in this case, R8 is the length of the payload. In this case, we are seeing just the left side 32 bits of R8. the right side, of R8, and this is passed in EDI, and EDI is then used as the length of the payload throughout the scan. If we zero out EDI, we will zero out the length, so MSI will just say, okay, this buffer contains no bytes, no need to scan it, and it will just break the execution. And this is how we patch MSI. For signatures, it's even easier to actually bypass signatures, because signatures are commonly used a blacklist approach. So if the payload match a signature is malicious, if it's not detected signature is clear. And sometimes just doing string encryption, so like we are encrypting all the string returned by our payload, is enough to bypass it. Like, it's not Mimikatz because it doesn't contain the word Mimikatz, right? But it's still dumping else as though. Well, it doesn't care because I'm stupid. I'm just seeing signatures, so I can, if it's not Mimikatz, yeah, not Mimikatz. So bypassing the sandbox instead is way more complex, and there are a few techniques around this. So what these techniques are about that, there is a very good research by Emeric Nazi, 7guess, the creator of MacroPack, very good tool. I would recommend actually checking it out. And so in order to bypass the sandbox, the AV sandbox, we can use a set of techniques. Some of them ranging from anti-debug techniques that are meant to understand if we are executing in a virtualized environment. And so in order to do that, we can use non-virtualized function, which are usually, so consider a sandbox is a very small VM. So I probably don't want to just create a full VM because it will take too much resources. So the AV create a very small VM with a limited set of virtualized functions in it, just in order to run my payload. So if we can understand what functions are not virtualized and we use them, we can actually break the execution if you are in a sandbox. Or we can do other things like checking if a debugger is active, or doing map section action, common anti-debug techniques. The other technique that we can use is resource disruption. Resource disruption is a technique that was working pretty fine like not long ago. And the aim is to try to allocate more resources than a sandbox can allow. So, for example, if I ask for 1 gig on the heap and I have a very limited VM, it will probably say, yeah, okay, you're asking too much, you need too much resources to run, I can't run it, just let's keep it. And another technique instead is logical disruption or logic deception, which is like using techniques that are impossible to achieve within a VM. For example, we know the user we are attacking, we just aim to that user, the VM will not be able to know what user I'm attacking, so it won't be able to actually continue the execution if I'm checking the name of the user I'm attacking, or some other techniques, checking the register or whatever. So something that I'm expecting in the real environment that can't be replicated in the VM. A technique usually implemented is actually to check if the VM is joined, is domain joined. For example, the check if the virtual VM is joined to a domain. If it's not joined to the domain I'm attacking, then it will break the execution. The antivirus can't actually replicate a domain and put the domain in the VM. So this technique is pretty much effective. And then we need to get rid of other thing, like we want to get rid of ETW, for example. ETW is a very complex piece of logic, I would say. So it's the Windows event trace actually record all events that a lot of events, and a lot of them are security related. AMSI as well as a lot of ETW events in it. So. And why we would want to get rid of that is because a lot of EDR are actually using the telemetry collected by ETW to actually correlate more information on the payload and classify it as malicious. So we want to get rid of this. So how we can do it? So in order to patch ETW, we are interested in two different kind of execution in ETW. The first one is event registration. Once a provider is actually registering an event that you want to trace in the Windows event trace registry. and the other one is the event write. So like when I am actually writing the event in the event trace. So in order to get rid of that, there are two main techniques. So one is patching with event write. The other one is actually, I think I'll need to skip a bit about this. The other one is just getting rid of all the event registered in a specific process. How does it work? So in event registration, we have this, we have full stack. So the event register we call the notification register, that will put the registration in a global registration table. And this registration table contains a list of to all the events that have to be logged within the process. So if we can detect, if we can get a pointer to this registration table, and this is usually achieved just looking in the process memory, in the process image memory space, using brute force, common brute force, because we know the registration table structure, we can actually brute force the process address space to locate this in memory. And we get an handle to that, and then we traverse this table to just call ETW event and register on all the event registered in this table. And this is one way to bypass ETW. It's a bit more complicated than in-memory patching, but it's also more stealthy because in-memory patching can be detected and can leave traces. And the other technique is the same thing we did with AMSI and DLL, we do with ETW event write, which is in ntdll. The patch is of course different and it uses a different kind of mechanism, but the technique is completely the same. And then userland in bypass. This is what we were talking about. And of course, when we talk about syscalls, manual mapping and all that stuff, we don't need to think that we have to do anything from scratch. Of course, we can rely on we can actually stand on shoulders of giants that created tools that can help us do our work. And these tools can be like using a static approach to locate syscalls or a dynamic approach to locate syscalls. Bear with me, I'll just explain in a second. So syswhispers is a tool created by I think Joru and actually and Jackson T. Yes, and so syswhisper one is a way to actually produce automatically a set of syscalls that you can just take and embed in your payload or malware. So it's using a static approach because it's using lookup tables. As John said before, every Windows version or build has different syscall numbers. So Joru did an incredible work of mapping all these syscall numbers throughout all the Windows builds, and syswhispers version 1 actually uses these lookup tables to build the syscall stub for us, given a Windows build. Of course, this technique doesn't scale well. So with time, dynamic kind of resolution was implemented using other techniques. So syswhisper v2 uses syscall called syscall number ordering. Syscall number, like locates all syscall numbers using export address table ordering. So it orders the functions, because the functions in ntdll can change their number, but luckily they don't change all the time. So they're pretty much the same functions. So if you use an ordering algorithm over the functions, you can actually detect the syscall number. It's a very smart approach actually. And then it has this part has two parts, like the syscall stub creation and an algorithm to locate the syscall number at runtime. And then you can just take whatever it's outputted by syswhispers, you can embed it in your payload and you can call syscalls that way. Another technique is, of course, manual mapping and else-gate. Else-gate is a very cool technique. It's still a technique to locate dynamically, not just the syscall number, but also the assembly stub is actually located at runtime. And these techniques are are implemented in Invoke, that also offers support for manual mapping, which is the one explained by John before, and overload mapping, which is like the same technique, just the difference is that the copy of ntdll in memory is backed up with a file on disk, so there is another section object in the process memory space with a file handle open to the file on disk, with like protected with sec image protection, but that's just niche to know. And then there is allosgate, which wasn't actually, I don't know any tool that implements that. Is a new technique by Sector 7, because else gate is good, but if the syscall stub is hooked, like the syscall stub, if the function is hooked, doesn't really work so well. So allosgate is a technique to patch dynamically, locate the syscall stub, locate the syscall stub, and patch it in memory if it's hooked. So it will just restore the original syscall stub if it finds a hook in it. Very cool technique. Check it out. It's Renzo by Sector 7. Very good. And then we want to blend with our target. This is a set of techniques that help us blending with our target more and being a bit more stealthy, even for ISIS, like that are actually seeing our payload in the file system, and even for antiviruses, because they will actually check also this stuff in our payloads. So one is metadata cloning, just actually cloning the metadata of a legitimate file can help us just being a little more stealthy, because we will actually resemble a real file on the disk. And the other one is code signing. Like, code signing the loader is a well-known technique to like avoid being overscanned, let's say, by an AV. Like, it's known that code signed binaries are less scrutinized by AV solutions. So we can code sign our loader, and that actually is a technique that works quite efficiently. But there are other techniques, like self-delete the payload in memory, like when you're executing something from file system, you want to self-delete it while it's running, or other techniques. There are a set of techniques, we don't have them all here, but there are a set of techniques that just help us being less, or not scrutinized at all, or just less scrutinized by AV, EDR, and also like ISIS of operators. And then let's bring a bit of automation, which is actually my contribution to this. So we created this tool, which is called Inceptor. As I said before, I'm pretty open to any suggestion, ideas, or issues, just open issues. So if you want to check it out and test it against your AV, your ADR, if you want to use it in your engagement, I don't know, maybe better in a test lab, just clone the repository, use it, and submit PR, whatever you want, because any help is accepted. So Inceptor is a template-driven framework, which can actually automate all the stuff that we were talking about, and as a way to abstract the shellcode in retrieval, so it can actually retrieve the shellcode wherever you want. You're not bound to have a blob when you're actually building your payload. You don't have to have a binary blob for the thing you want to execute, but you can embed it within an icon, a research, a PDF downloaded from internet, whatever you want, because Inceptor can abstract the way you recover your shellcode. It has automatic encoding. Automatic is not really true. Like, you can set what kind of encoding you want. Inceptor differentiates between loader-dependent encoders and loader-independent encoders. Loader-independent encoders are shellcode-based, so they will actually decode your shellcode after you injected it. And it's good, but it's not suitable for things like assembly load or like PE manual mapping, because, of course, if you're mapping a PE, you want to have a PE. If you just encrypt it, it's not a PE anymore, so it doesn't make sense. You have to decrypt it before mapping it. And so I also developed these loader-dependent encoders that are just encoders, the same way as loader-independent encoders, but are dependent to the loader. So the loader will actually be aware of how to decode the stub before injecting in memory. And then there is automatic obfuscation. The native obfuscation is performed by using LLVM compilation. The .NET obfuscation is based on Confusery X or other public available obfuscators. And PowerShell obfuscation is obtained through Chameleon, which is a tool I developed, but you can choose your own tool. Doesn't make any difference. You just need to create a little interface for it, and you can use it. And then Inceptor also provides ways to automatically patch MSI, Windows lockdown policy. Well, we didn't talk too much about that. WLDP and ETW in memory before doing anything else. And it offers a way to compile automatically and pack it, offer a few different compilers. It has a wrapper for MS Build, CSC, CL, Clang CL, and LLVM CL. So it offers for automatic compiling and packing. It also can pack .NET binaries, which are built on top of other DLLs. So it's pretty suitable if you have just a DLL that is working and you just want to use that in your malware. It's fine. It automatically compile it. And then it has also techniques to blend with the target. So all the techniques about metadata cloning, code signing, self-deleting, and other techniques that I don't recall at the moment are already present in the tool. And we are actually implementing more and more stuff with time. As I said, if you have anything that you want to actually add to this tool, any improvement, please reach out, because I'm working on, of course, in my spare time, and yeah, it's tough. And that's it. We have first maybe a little demo to So this is a little demo about Inceptor, and it's just to show that Inceptor can automatically provide support for the Invoke. You just need to specify like a few parameters when you're generating your payload. So here we are just generating a meterpreter kind of payload. And after that, we pack it using Inceptor. And the first time, we'll just pack it using a common classic pinvoke kind of thing. So I don't know why this is spawning. I did it this way. So first run, no invoke, syscall. Nothing at all. We just have the pinvoke routine. So pinvoke, as we were saying with John, can be detected by userland hooking, because we are just statically importing the function we want to use, and so we are detectable both by using IAT hooking or inline hooking. Doesn't matter. We just detect it because every function that we import will be present in our import address table. So now we're just using Frida, which is it's not an EDR, of course, but it's still doing the same thing that the EDR does. So it's install hooks on the function that we want to hook, and as you can see, the payload executes. We have a shell, but we are detected. So an EDR doing the same thing will just say, "What are you doing? You're creating a thread. I'll stop you." Yeah, this one I want to explain. This one was a mute video. So in cases when I can't actually speak, I also added this just to let you understand more. In the second case, what we want to do, we will pack the same meterpreter payload, but we will use the Invoke. I don't know if it's clear actually, if it's seeable. So yeah, here we are just deleting the file, and we are returning to Inceptor, and then we use the Invoke. Sorry, it's not seeable. We're using the Invoke module to generate the payload. This will actually help us using another template, which is the Invoke manual mapping here. So we will use manual mapping this time. It's the same kind of payload, just packed using the Invoke. And the same thing, the notepad will be spawned, and the notepad is just the payload, the sacrificial process we spawned to actually inject into it. And then this payload will inject into notepad and start the handler. And yeah, we have a shell now, but we have zero detection by Frida. Like the call 20 create thread X was not called. And the reason why it's not called is because we used the nt create thread X inside the manually mapped ntdll. If you're wondering how this works, it's just, we're just locating in memory, we're just getting an handle to our module in memory, and we just have to detect the function in that module. So it's just a matter of scanning the process memory in the right location till we found the function pointer that we want to execute, and then execute it. And that's it. We have it. Yeah, it's finished. Yeah. And thanks for listening so far, and hope you enjoyed that, and have a nice rest of the day.